All right, so in this part, we'll take what we learned about probabilities and we'll apply them to probability density functions. So the first thing that we need to understand is the difference between discrete and continuous random variables. We were introduced to the concept of random variables in the last lecture, essentially variables that are some amount of expected values between a range. But I threw around the terms discrete and continuous and didn't really go into what they meant. So a discrete random variable is made up of distinct and separate outcomes. It's like the coin flip experiment. There were 2 potential outcomes there, or in a dice experiment when there would be 6 potential outcomes, or however many sides the dice has. You can always count the number of things, count the number of sides, count the number of flips, but there is a discrete, countable set of outcomes. And the binomial distributions that we discussed last week are discrete. There's always a countable number of expected or observed outcomes. In contrast, continuous random variables can be any values within a range. Continuous data is usually measured rather than counted by a ruler or a speedometer or a scale or something that can, in theory, have infinity possible values between 2 bounds, right? Like you could measure 3.99 as a weight, or 3.99999 as a weight, or 4.111. There's infinity numbers between any 2 bounds, and so that's what's meant by a continuous data set. So we haven't encountered any continuous distributions yet, but we will. The normal distribution is what we'll use for the majority of this course, and we'll be introducing that in a few lectures. So let's explore a little more about the differences here. So when you sum a range of outcomes in a discrete distribution, we already kind of covered this, right? So if the probability of getting a heads and then a tails and then a tails and then a heads, right? We added those 2 together when we were trying to say, all right, what's the probability of either getting a heads and a tails or getting a tails and a heads? So when you want to sum a particular range of discrete outcomes, you simply add up all of the probabilities that equal the values within the range. So for example, if we want to see what the probability of the random variable being between 11 and 13, we would sum up the probabilities of it being 11, 12, or 13, 0.16, 0.12, 0.037, and 0.353 would be the sum of all 3 of those, and the probability of being any of those 3. But what if it was a continuous distribution? We couldn't really add up things in a continuous distribution because there's infinity possible things inside of there. So continuous probability distributions are a little bit different. Continuous probability distributions fit continuous data, as we've said. They're also known as probability density functions. And so probability density functions show the likelihood of getting outcomes within a range of possible outcomes for a continuous set of data. So say we were measuring the height of a group of people, and we put it in the form of a histogram, which is we have a range of heights and then brackets between which we count how many people fall into that bracket, and that gives us a distribution of heights across a range and with a number of measurements. So we can fit a smooth curve to this data, and this smooth curve fitting the data would be known as a probability density function. It has some rules, and those rules mimic what we were discussing for the discrete probability function, the discrete probability density function for binomials. So remember that for discrete outcomes, if you added up all of the potential outcomes, all of the potential expected outcomes, it would equal 1. So for probability density functions, the area under the curve ends up being 1. Or for a random variable x, a function of that variable, if you take the integral across the entire function, which would be all of the area under the curve, it will equal 1. And so I don't know if you've had integrals in some of your other math classes. If you do, hopefully that helps you understand this better. If not, don't worry about it. Just know that for probability density function, all of the area under the curve has to equal 1. So what if we wanted to sum a range of potential outcomes in a continuous probability density function? We just looked at it for the discrete case. For the continuous case, for the discrete case, it was summing up all of the potential outcomes. And for the continuous case, it's just integrating all of the across the range that you want to find probabilities for. So say we wanted to see what the probability of getting a height between 4.9 and 5.5. That would just be the area under the curve between 4.9 all the way up to 5.5. And that's illustrated by this red block here. And it would be an integral from 4.9 to 5.5 across whatever the function is that describes this curve. So that's how discrete and continuous kind of relate to each other. One has these summations, the other one has the integrals. All right, so I drew a hypothetical, very squiggly, because I don't have a steady hand, probability density function for the age of redbud trees in New Jersey. There's a lot that are around 25 and 30 years old. I totally made all this stuff up. Don't worry about it. It's just the fact that this is a probability density function. And underneath this function, I've put what the probabilities are in each of these regions between 0 and 15, between 15 and 20, 20, 25, 30 to 35, and 35 plus as 0.07, 0.18, 0.24, 0.26, and 0.21. So basically done the integrals for you. So what if we had an example question that was based around this hypothetical probability density function? And we wanted to know, all right, what's the sum of the area under the curve? Well, as we talked about in the previous slide, the sum of all of these values would be the sum of the area under the curve. And if you add all these up, you're going to find that that is 1. And that's always the case for all probability density functions. So what if we asked, well, what's the probability of a randomly sampled tree will be older than 25? So we'll be in this region here. So if we wanted to know what that would be, we would have to sum up or integrate from 25 all the way to infinity. And in this case, that would just be adding 0.26, 0.21, and 0.04 together, which would be 0.51. So this yellow is the area under the curve, and these are the numbers that correspond with it. So what about asking probabilities for a sample tree will be older than 15 but younger than 25? So again, we would look in that range for the area under the curve, and since I've given you the numbers here, you'd just be adding them up, and this would equal 0.42. I hope this is all starting to make sense with the way this works under a curve. It's very important for when we're discussing normal distributions, because we'll constantly be thinking about the area underneath the normal distribution curve to figure out p-values and all the things we need for statistics. Okay, here's a tricky one. What's the probability a randomly sampled tree will be 20? So it's a bit unintuitive, but the answer is 0. Because if you were to say, well, what's the probability it will be between 19.999 and 20.01, then there would be an answer. It would be very small, but it would be an answer. But since 20 is a single line, the odds of you getting a tree that is exactly 20 years old to the second, to the millisecond, to the nanosecond is always going to be 0, because you're integrating across a range of 0, and therefore it's going to be 0. So with continuous distributions, you always need a range in order to derive a probability from the probability distribution function. All right, so now let's go through some even harder questions that integrate what we learned about probability trees with this newfound area under the curve for probability, continuous probability density functions. So question 1 would be, what is the probability of the first sample tree being below 20 and the second one being above 30? You shouldn't have to draw a tree for this one, but if you want to pause the video and try to figure it out on your own, you can. So in this case, the probability of the first tree being, the probability of a tree being above 20, the probability of a tree being below 20 is 0.18 plus 0.07, which is 0.25. And the probability of it being above 30 is 0.21 plus 0.04, which is again 0.25. So if we want the probability that the first sample tree will be below 20 and the second will be above 30, then we're simply going to be multiplying 0.25 by 0.25, because these are two independent probabilities, so we multiply them together to get 0.0625. All right, so here's a harder question. What is the probability of one tree being below 20 and one tree being above 30? This time we don't care about the order. The first one I said, the first one has to be below 20, the second has to be above 30. In this case, it doesn't matter the order, just one of the trees has to be below 20 and one of the trees has to be above 30. And so for this one, you will need to draw a probability distribution, and it will be the biggest, you will need to draw a probability tree, and it will be the biggest one that we've drawn so far. So you can pause here. Okay, and so the solution is as we've stated in the first part of the problem, being below 20, there's a 25% chance. Being above 30, there's a 25% chance. And here in the middle, 0.24 plus 0.26, there's a 50% chance that the tree is between 20 and 30 years in age. And if we, so in order for the tree to be, one of them to be below 20, we could say, all right, the first one's going to be above 30, and then the second one can be below 20. If the first one is between 20 and 30, then there's no way for it to satisfy our potential things here, because one has to be below 20 and one has to be above 30. And if we look over here, if the first one's below 20, then it's going to be the second one being above 30. And I've written in red what all of the multiplied probabilities are. So 0.5 times 0.25 is 0.125, 0.5 times 0.5 is 0.25, just like we did in the other probability tree. And so what we're looking for here is either the first one being below 20 and the second one being above 30, or the first one being above 30 and the second one being below 20. And that's the only way to satisfy our stipulation of one tree being below 20 and one tree being above 30. And so we would add these two probabilities together, 0.0625, and then we've got 0.125. So that's how you would approach this with a probability tree. All right, so what should be the takeaways from the two lectures this module? The first big one is things on probability. You want to know what probability is and its relation to frequency. You want to know what the probability rules are for both discrete and continuous data. And we care about this because it's the core of statistics. All the concepts in statistics relate up to this one of how likely events are to occur. And we're going to use it again constantly, and specifically we'll use probability to derive p-values, which are slightly different later in the course. You'll just continuously use these probability rules over the course of this course and your life. Discrete versus continuous, it's an important definition. You should know it so that you know the difference between discrete with a set number of outcomes and continuous with infinite outcomes. And we'll use this terminology continuously throughout the course. Binomial random variables. So you want to know how to identify a binomial random variable. You want to know how to use the equation for the binomial random variable. And we care about this because it's the first statistical distribution you're being introduced to. It's not used so much in a lot of biological research, but a modified version of it, the negative binomial distribution, is used for a ton of biological applications, from RNA sequencing to Bayesian modeling. And essentially, the negative binomial is, instead of holding the number of trials constant, it holds the number of successes constant, and then allows the number of trials to vary based on what the probability is. And so we won't build off it much more in this course, but it's always useful when you do encounter a binomial random variable, such as a coin flip experiment or things of that nature. Probability trees are extremely useful. Know how to make them and use them. I still use them when I encounter problems with discrete number of outcomes in lab, with mating schemes. They're just a very intuitive way to deal with probability at all times. We'll use them again indirectly, but I don't think any of the later statistical tests will build directly on them, but they're just very useful in general. And finally, probability density functions. They're a core concept for analyzing continuous random variables. We really care about them for this course. We'll be looking at a normal distribution for most of the second half of the course, which is extremely important to all of science, and we'll be using it again constantly. So make sure you have a good feel for these concepts that are introduced, and we'll do some exercises in the classes coming up that will allow you to get a better feel for solving some complex problems.